Alright, video lecture 2.2. In video lecture 2.1 we looked at SI units and we looked at conversion factors, and hopefully those are coming along nicely. In this section we want to look at our old friend scientific notation. Now I know you've been exposed to this to some degree. Hopefully we won't have too many troubles with this, but it is important. We will deal with a lot of numbers in scientific notation. So what is scientific notation? Well, it looks like where you have a number m times 10 to the nth power, and so we need to make we need to define some things here. For one, m, that number out in front, we call it a coefficient, and that number needs to be between 1 and 10. It can be equal to 1, but it needs to be equal or greater than 1, and it has to be less than 10. The main idea is that we have a number 1, 2, 3, 4, 5, 6, 7, 8, 9, and then the decimal point, and then the rest of the number. And so that's what we're seeing here. Also, the n, which is the exponent, has to be an integer. It could be a negative or positive number. It could also be 0, depending on what we're dealing with. Now, if the exponent is 0, it's really no sense in putting the scientific notation there. It means that there is no shift in the decimal. First, we want to take a look at shifting a number from long form into scientific notation. If you're dealing with millions and billions, numbers that large, this makes a lot of sense to change those. We will have to be able to change a number from scientific notation back into long form sometimes. I'm not going to cover that in this video lecture, but ultimately it's just the opposite process of what we're doing here. So our first step, we need to determine our coefficient. We need to determine that number out in front. So we take the number we begin with, whatever it might be, 58 million, and we move the decimal to where instead of 58 million, it would be a number that's between 1 and 10. In that case, it would be 5.8. Our next step then is to figure out our exponent. So we only have 2 steps, pretty simple. We needed to figure out our exponent by figuring out how many places we moved the decimal and which direction we moved it. If we moved it left, it's positive. If we moved it right, it's negative. Some of you may know a little bit about nursing, and there's a silly acronym that you can use here that might help you to try to remember this. I have another way to look at this, but if you know that there are a couple basic types of nurses, there's an LPN and there's an RN, licensed practitioner nurse, I think, something like that, and then the registered nurse, I'm not positive, but you have the LP and the RN, and that's kind of how I tend to remember this. If we move the decimal left, then the exponent's positive, LP. If you move it right, then it's negative, RN. So if you're familiar with nursing, the LP-RN thing might work for you. Another way to look at it is if the number's large, our exponent should be positive. If the number's really small, our exponent should be negative. That's the route I tend to go, but it doesn't matter what works for you. Here we see the example. I want to walk you through it briefly. We start with the number 4,630,000. That's several extra zeros that we don't really need to write. So to convert it into scientific notation, first step you see in purple there, you need to move the decimal to make the number between 1 and 10. And to put it between the 4 and the 6, 4.63 is between 1 and 10. That's our first step. Then we determine our exponent by figuring how many places we moved it and which direction. Here we moved it 6 places to the left, so if you remember LP, left means positive, or if you notice that it's a very large number, should have a positive exponent, we see it as being a positive 6. So our answer is 4.63 times 10 to the 6th. Again, what they're showing here in yellow is that the original number was greater than 1, so the exponent is positive. Again, it's a big number, bigger than 1, it's positive. If it's less than 1, it's going to be a negative exponent. Here's another example. The reason I do this is that you can see the decimal point here. This is a number 65 million. Kind of like I mentioned 58 million before. This fits the same idea. We need to move the number or the decimal to make this number between 1 and 10. Between the 6 and the 5, 6.5 would be between 1 and 10. And then we need to count how many places we moved it. Clearly, you can see there that there are 7 moves, and it's to the left. And so left positive, right negative, or again, the number is large, so it requires it to have a positive exponent. So 6.5 times 10 to the 7th. Now, hopefully that's a review. Hopefully that's not too bad. If you have issue with that, please come talk to me, and we can work it out, I know, with a little bit of time. But the last thing that we want to mention here is the mathematics involved in scientific notation. This is the part that can get a little tricky. I want you to try to remember things in terms of fractions. If we're going to add and subtract fractions, say 1/2 and 1/3, I can't add them until they have the same common denominator. And so we would convert both fractions to be in the form of sixth, and I would have 3/6 plus 2/6 instead of 1/2 plus 1/3. Then I'm able to add them together. With numbers in scientific notation, there's a similar feature there. Instead of having a common denominator, they need to have a common exponent. I can't add 2 numbers in scientific notation unless the exponents are the same number. And so we have to adjust one of the numbers to match the other one. It's your choice what you want to do. I think a general rule of thumb is that it's most of the time better to increase an exponent than decrease an exponent, but you can do it whichever way you would like. There's one other step, is once you get the exponents the same, all you have to do is deal with the coefficients like you would if the exponents were not there. So you simply add them or subtract them. Again, the key thing is that you have to have the exponents the same first. And this is similar to adding and subtracting fractions. Once you get the common denominator right, you simply add or subtract the numerators depending on your process. So let's see an example here, and please don't jump ahead, just follow me through. We have 2 numbers that we're adding, 3 times 10 to the negative third and 2 times 10 to the negative second. So the problem is that the exponents are not the same. You have to have common exponents. So in this case, we are going to take the smaller exponent and increase it to match the bigger exponent, negative 2 being larger than negative 3. And so in this case, they take 3 times 10 to the negative third. If I want to change the exponent, I have to add 1. Now remember, when we're changing the exponent, what we're doing, you'd say, well, if we add 1, that's a positive move. But in this case, by changing the exponent to make it larger, we need to make the number out in front smaller. And so that's kind of an adjustment that we'll have to kind of look at in class if it doesn't make sense. But the key thing with the number in scientific notation, however you change the exponent, you change the coefficient in an opposite way. So if the exponent gets bigger, the coefficient gets smaller. If the exponent gets smaller, the coefficient gets bigger. In this case, we had to make the exponent bigger by increasing it to a negative 2, which means we had to make the coefficient smaller. Again, the LPRN works here as well. We had to make a positive change to the exponent by adding 1 to the negative 3 to get it to a negative 2 power. By making a positive change to the exponent, we move the decimal to the left 1 place. However that works for you, I want you to kind of figure out your best way to understand this. I'm always going to try to present it in more than one way. And if this is confusing, again, we'll talk about it when you get to class. Come with questions. But once you get the exponents the same, they're both to the negative second power, the exponent stays the same. It stays at that negative 2 power. All you have to do is add the numbers in front, the 2 and the 0.3, and clearly we get 2.3 times 10 to the negative second power. And you will have to do this, you will be required to do this, and you won't have a calculator for at least this chapter on this. So we do need to learn how to work with these numbers, and of course homework will be practiced for that. The last slide I want to mention is multiplication division. This is much easier than addition and subtraction. In this case, if we want to multiply fractions, we don't have to worry about getting common denominators or numerators for that matter. We simply just multiply the numbers straight across the top and straight across the bottom. In scientific notation, there is some ease with this. The first step, however, is now we're going to deal with the coefficients first. We just multiply or divide them, whichever operation we're dealing with. The exponents, however, here's the trick we have to remember. Multiplication is to division like addition is to subtraction. And so when we multiply numbers, we add the exponents. When we divide numbers, we subtract the exponents. And you notice here in parentheses it says top minus the bottom. We're going to set up our division in terms of a fraction. We talked about fractions in the last video lecture. We're going to deal with a lot of fractions the rest of this year. So I would adjust that if you're not used to writing things as fractions. When you write x divided by y, get into that habit here. It's much more visually appealing. So let's stay on the left side with multiplication right now. We're going to multiply those two numbers on top. Remember, we don't have to deal with exponents here or worry about, or we do have to deal with them, but we don't have to worry about them so much. First, just multiply the coefficients. The coefficients are 2.5 and 5. Just multiply them, and we end up with 12.5 as our coefficient out in front. Then, since we're multiplying the numbers, we add the exponents. We add 17 and 14, and we come up with 31. Now, if you look at the very bottom, you'll see our result. Multiplying the coefficients gives us 12.5 times 10 to the 31st power, and the 31 comes from adding the exponents. Now at the bottom, though, this number is not finalized. It's not correct scientific notation. That front number, that coefficient m, needs to be between 1 and 10, so we need to move the decimal 1 to the left, which means we have a positive change to the exponent, and so we add 1 to the exponent to get it to 1.25 times 10 to the 32nd power. So now we look on the other side with division. We're going to divide those same two numbers. And so 2.5 times 10 to the 17th divided by 5.0 times 10 to the 14th. Again, deal with the coefficients first. Let's keep it simple as we can. Divide 2.5 and 5, and we get 1/2. Now as we start to look on the other side, we see the exponents. And when we divide, we do top minus the bottom. This is why it's beneficial to write it as a fraction, because you know which one's on top. You don't have to guess which one to start with. We start with the one on top, 17, minus the one on bottom, which is 14, and we get an exponent of 3. And so we have 0.5 times 10 to the third. Here again we need to adjust our number because 0.5 is not between 1 and 10. So we'll move it 1 to the right, which means a negative change to our exponent. Again, you could look at it that way, or you could say I'm making this coefficient bigger to go from 0.5 to 5, which means I have to make my exponent smaller by however many decimal place moves I make. And so we end up with 5.0 times 10 to the second power. These aren't the easiest things to explain in a video lecture. If it seemed too much too fast, listen to it again. This is not that long of a video lecture. Go back, go through it 2 or 3 times, rewind it. And if you still don't have it, then definitely come and do not be hesitant to ask questions. We will need to practice this, I think, for most of us to get it down correctly. That's it for video lecture 2.2.